Log on, tune in, find out. Another good idea from Cambridge.
From GMP/SAS, and Brad's title is there, so I'll let him get going. But I know that people have been dying for more software stuff, so I encourage you to call Brad at home anytime. If you have any questions, just do that.
Gee, thanks, Derek. I'm going to talk today about something that's not quite the same kind of thing that people have been talking about so far in this conference, because I'm going to consider designs that actually do have noise involved in the response. And think about a question that I got after a talk that I gave on computer simulation design, where I talked about the various kinds of space filling designs that you might have. And somebody in the audience said, well, this is very interesting, but here we have this big body of knowledge about designs that we do when we have lots of noise, the fractional factorials, factorial design, split plots, all of that body of knowledge. And then we have this completely different set of rules for designs that have no noise. And the question was, what happens on the continuum between lots of noise and no noise? Is there just this big jump, a quantum jump from two-level designs to just fill up the space? So that made me start thinking. So Latin hypercube designs are the designs that are kind of the default. Everybody talks about Latin hypercube designs for deterministic computer simulation. And when we're doing at least industrial experimentation on physical processes, factorial designs tend to be the standard. So the thing that everybody likes about the Latin hypercube design is this uniform one-dimensional projections. So no matter which dimension you're talking about, the points all fall uniformly on the line on that projection. This is what the 1D projections look like for two-level factorial designs. And we see everything falls on either one point or the other point, and then there's a lot of built-in replication. And that built-in replication is actually a feature. And that's what allows you to reduce the variance of the differences in means. And that's what Fisher was so excited about these designs. And so that's what makes these designs so good when you have noise in the response, is that you reduce the noise through this sort of virtual replication. So, looking in two space, then on the left you can see the factorial design, and I made just a tiny little bit of jitter so that you can see, I'm in two space, and I have eight points, and each of the 4 points at the vertices of the square are replicates. Whereas in a Maximin Latin hypercube, there we see that it kind of seems to fill up the square in some way. So we have some pros and cons for the two kinds of designs. The pros for factorial design is they're good for precise parameter estimates, and that's precise meaning when you have variance, you lower the variance of the parameters by using these designs. And they're really good at predicting when you have a first-order polynomial approximation. A two-level factorial design can't do anything about detecting curvatures because you only have 2 points. And replication is completely useless if there's no noise. You just get the same function value over and over again. The Latin hypercube, on the other hand, is good for detecting and modeling curvature. It's good for integral approximation. In fact, that's what they were invented for. It's very inefficient for estimating things if there is noise, and less powerful for modeling interactions. And I'll talk more about that coming up. But the thing that worries me is that because computer simulation design has become pretty popular, and because Latin hypercube designs are sort of the default, the standard for doing these things, then a lot of engineers are starting to do Latin hypercube designs to model systems with substantial noise. And that is a less good idea. So let's look at let's suppose that we do have noise, and let's suppose that we in fact used a Latin hypercube design instead of a factorial design. Well, I've looked at 2 through 5 factors here, and for each number of factors I consider a 16 run design and a 32 run design, and I create a Maximian Latin hypercube and a 2-level factorial, and compare the relative efficiency of the Latin hypercube design to the factorial design just for the main effects model. And you can see that as the number of factors increase, the relative efficiency drops from the 60s to below 50%. And it gets even worse, in fact, much, much, much worse if you have interactions. So here we have 6 factors and 32 runs with an interactions model. On the right here, you see the variance of the betas for if you were to do a 2-level factorial design, and they're all 1 over 32 for every beta. But for the Latin hypercube design, which is the variances on the left here, the main effects are being estimated about 3 times worse than the main effects are being estimated for the Latin hypercube design, and about 10 times worse for the 2-factor interactions. And that's parameter by parameter. So you can see that if you do have noise, the Latin hypercube design is really going to cost you if you use it. So if you have a deterministic response model, you're really only concerned about the bias between your simulation and your emulator. Actually, you probably should be concerned about the bias between your between reality and your simulation too, but I'm not going to go there. Or I just did, didn't I? When the noise is larger than the signal, then prediction variance becomes a primary concern of your modeling, because you're not going to be able to detect small changes in the function amidst large noise. The best you're going to be able to do is get some sort of first order knowledge about the system amidst all that kind of noise. So there's not much point in worrying too much about small biases and curvature in those cases. But when the noise is smaller than the signal, then it makes some sense to think in your design construction about both variance and bias, and try to figure out how you might trade off there. And that's the motivation for this bridge design idea. It has high D efficiency, or actually high variance efficiency, because you don't have to use D efficiency as your variance criterion. You could use any kind of variance measure, and at the same time, there's no replication in projections to one-dimensional axes, so that you can do Gaussian process model fitting even even if there are a substantial number of factors that don't have any effect. So the implementation approach is an algorithmic one. You find a design that minimizes some variance measure subject to a minimum projection distance between coordinates. And this is actually motivated quite a bit by Detta and Papelishev's paper in Technometrics, where they consider Latin hypercube designs. They start with a Latin hypercube design, say a max and min one, and then they apply a nonlinear transformation to the x's so that it pushes the points out towards the edges of the space, so that instead of uniform one-dimensional projections, the projections look kind of like a curve, where there's high density towards the edges and small and lower density in the middle. And their argument is that most of the space in a hypercube is towards the edges of the design and not in the center. I thought that was very clever, and so I was thinking, well, if we are willing not to have absolutely uniform projections in 1D, then there are lots of other things that you can do, and that was just one. So here's my optimization problem. Let's maximize, for instance, the determinant of x transpose x, where x is some model matrix for a polynomial model, say, and subject to the inner point distance in any dimension has to be, in any projection, has to be greater than some minimum value. So what that requires is a number of design points. You have to decide on what polynomial model that you're going to use as a basis for doing the variance calculation, and then you have to decide what is this minimum distance going to be. If the minimum distance between points is very, very small, then you get something that looks very much like a d-optimal design, because the points will crowd close to the points where the d-optimal criterion would put them. And as you increase that inner point distance requirement, you get something that's closer to a d-optimal Latin hypercube. So that the set of designs creates this bridge between the two criteria. So I'm thinking about this betrays my own training, which is more physical experimentation. We think between -1 and 1, and not between 0 and 1 in the in the cube. If you're going between -1 and 1, then the Latin hypercube has coordinate distances of 2 over n minus 1. So if you had like 21 points, then they would be spaced at a distance of 0.1 apart. If you were going between 0 and 1, you can just get rid of that 2 in the numerator. The factorial coordinate distance, of course, is 0. We get lots of replication with factorials. And so halfway is kind of is another thing you might think about as a way of seeing just what this criterion kind of does. So here's some kind of interesting things that happen. One is, if you make the polynomial model be a main effects model, and your factors are all quantitative, then what the criterion wants to do, especially if the inner point distances are small, is it makes little x's that, in two-dimensional projections, you have an x of points, and then space in the middle. That really doesn't look very nice. But on the other hand, it may allow you to, in some ways, actually do better. But it's hard to convince a referee of that. So then you say, well, of course, if you add quadratic terms to the model, then you will automatically enforce at least three support points in every dimension, and then the points will cluster around those 9 points instead of just the 4 points at the corners. And you could, I mean, you could even do cubic polynomial as your basis model, and then you'd have 4 points in a grid for each case. So here's a bridge design on one side and a Latin hypercube on the other side. Here the bridge design has a minimum distance. There are 8 points. So the minimum distance for the bridge design is almost as big as the minimum distance in the Latin hypercube. And you can see that they look somewhat similar. But if I make my inner point distance smaller, then you start seeing that X shape. This is for the main effects model being the model that you're looking at for variance. If you want to avoid the X shape, you can use quadratic terms in your polynomial model. I still think you can see a little bit of the X behavior at the edges of each of these two-dimensional projections, but it's not so pronounced. And you can also see that the correlations among the variables are very small, so these are nearly orthogonal designs, which is something that you would expect if you're minimizing variance for a polynomial at the same time as maintaining this distance criterion. So I took the sample test function from Detta and Papelashev in 2010. This is their equation 6, and it's an 8-factor example. You can see that the functions are kind of complex. They're as you go from x5 through x8, there's more and more flatness for each factor. The main action is happening in x2 and x3 here. When I used the full quadratic model for my model underneath my design, I used an 80-point design just like they did. And so they compared their design to a Maximian Latin hypercube design. Their design, recall, pushes points out towards the edges, and they beat the root mean squared error of the Latin hypercube design by a factor of 2, and for a deterministic response. And the bridge design that I had, I don't think that the difference between 1.4 and 1.3 is particularly meaningful. I wouldn't say that the bridge design is better than their design in any case. It's just one example after all. So to summarize, bridge designs are a tunable family of designs that sort of span a space between Latin hypercube designs on the one hand and variance optimal designs on another. They would allow for, if you have noise, they'll allow for efficient polynomial estimation. And but since there's no replication, even in projection, you can still fit a Gaussian process model so that you can have either kind of model. And by using higher order polynomials as your base model for computing the efficiency, you can make these designs be very space filling. So that's what I wanted to say about bridge designs, but I also wanted to talk a little bit about something else. Rosemary gave a really interesting talk at the end of the week last week. If you weren't here, then I'm going to talk a little bit about her problem, which was, suppose you have plots of land in a grid, and so there's rows and there's columns, and you're going to plant these rows and columns with various varieties of seeds. So each square there is going to get a different seed variety. And suppose that you think that there might be fertility gradients across the big plot there. You don't know exactly what those gradients might be, but you suspect that maybe a second order polynomial might be adequate to describe that gradient. Now, you can in her problem, what she said was, let's choose 56 of these 280 plots with control seed, and so they would all be the same. So the only thing that you would be observing on these control plots would be the gradient effect. And so how would we assign the 56 plots in order to get the most information given a quadratic model? So here's the d-optimal non-replicating design for the full quadratic. So the d-optimal design for two variables and a full quadratic model on the square would put 8 points at all the corners and I believe 5 points on the edge, the centers of the edges. So that's 32 plus 20 is 52, and about 4 points in the middle. So what's going on here is that it can't do that. It can't replicate those points because I'm requiring that each point has to go into a different plot. So this is very similar in spirit to what I was just talking about, except instead of not replicating in projection, I'm just saying I'm making the less restrictive, I'm making a smaller restriction that just you can't replicate a particular point. And there's a certain distance that points have to be apart in space, but you don't have to project them and not get replication. So this is the d-optimal design, and this is the I-optimal design. So the I-optimal design, if you were not if you're not making this restriction that you aren't allowed to replicate, would put 16 points in the center, and then evenly spaced around the edges. And so we have 16 points in sort of a grid in the center here, but and then covering the edges in other ways. I think that this kind of design is actually something that might be really useful in a lot of other situations where you don't want replication, and you want lots of levels because you want to be able to get curvature, but at the same time you may not want n levels for every factor. In fact, it seems to me that the n levels for every factor's restriction is way too restrictive. So that's all I have to say. Oh, except that the d-optimal design is 85% or 87.5% I-efficient, whereas the I-optimal design is 96.5% D-efficient. And so I would probably choose the I-optimal design myself.
I think I strongly disagree with you. I think. Yeah. Your starting point is deterministic versus random. I disagree there because my starting point would be I'm going to fit an emulator, a meta model that's either a low order polynomial or a Gaussian process. If it's a low order polynomial, whatever the noise is, zero, medium or big, I will end up with Plackett-Berman design. If it's a first order polynomial, if it's a second order polynomial, I probably, for practical reasons, would settle for central composite design. But if I decide that it will be a GP, and so I even don't need any replication if I assume substantial noise, but I assume at the same time that my low order polynomial is adequate, because then I use the mean squared residual. It's a better estimate on replication. I can prove that. On the other hand, if I decide to go for a more complicated meta model, and people in deterministic simulation, what I remember, hated the polynomial because it didn't fit the true answers. And the GP does fit, is an exact interpolator. But once I decide to go for the GP model, what you call GASP, I understand, then I probably settle for Latin hypercube sampling. Now, starting tomorrow probably, we have GP models for situations with substantial randomness, and then we probably will introduce some randomness with various, or some replication there. So I might start to summarize, and I think that Susan Sanchez and I, we published an article in Journal on Computing, where our starting point is it determines on how you are going to analyze your simulation data. Are you going to analyze it through low-order polynomials? Then you go for factorial designs. Or are you going to analyze it through, for example, GP, but maybe if you are going to use a neural network, that hasn't been mentioned yet, maybe you also go for Latin hypercubes. So we are very different. So the amount of noise enters much later in the discussion. So that's why I think I disagree.
I suppose that if you want to have some leeway as to your decision about what emulator you're going to use, whether it's a low-order polynomial or a GP, then if you chose the Plackett-Berman design, you're not going to be able to fit the GP. So that kind of rules that out. And so I chose to think in terms of spanning the notion of noise and dealing with variance and bias. Perhaps that's not the best way to view this problem, but I think that there needs to be some larger framework into which we view the issue of going from noise to no noise, and why we make the design decisions that we do. So this is an attempt at that.
Can I follow up on that? So this discrepancy here,
Which makes it interesting.
I think the issues are actually connected, and I think one thing that Brad said earlier was a philosophical statement that if you have a lot of noise, you're not going to have the resources to capture a complex shape. And so then a Gaussian process model doesn't make sense. So something more going far beyond linear approximation might be all you're able to do. So the data situation is what's driving this, not the model. So the data drives the model choice. So, okay, I've got data with a lot of noise. I'm not going to go with a Gaussian process model because it's just too much noise. So that's when he talked about the signal to noise issue. So I think the data structure is driving it, and that leads you to both the model choice and the experiment design, maybe.
But then you could say that problem too much noise by doing replications.
So I think this is probably a good conversation over beer, so we can get to the next one. And listen, I tell you what, there's a pub down the street called a Punter. Brad will buy. All right, so let's thank Brad again.